friends, welcome to part 3 of our video presentation on chapter 3 that deals with telecommunications and networking. In this part we will talk about different types of network topologies and also different types of networks in general, different ways of connecting devices together as a part of a network. Now, a network topology is a configuration or arrangement of the devices that are part of one single network, and there are several ways to arrange those devices. One topology is called bus. It means all devices are attached to one cable. It looks something like this. So here we have a cable, and here we have individual devices being linked with the help of this cable. Now, it's a simple, quick, and efficient way of connecting devices, but there is one big problem. There is a single point failure problem, meaning if there is something happening with this bus right here, let's say there is a disconnect or some kind of damage, then other devices, they won't be able to reach devices that are part of that bus configuration topology. So basically this kind of arrangement is very prone to damage. Then you have the so-called ring topology. It looks something like this, where devices are connected into one single ring. Now, it's not prone to a single point failure, because if there's some kind of damage here, let's say, then the signal, instead of traveling this way, it can travel around like this. But still, if there is two-point damage, then it can lead to the problem of devices not being able to send messages across the network, at least some of the devices. Then there is a start topology. It means all nodes are attached to a central device. Here you have central device, and all computers or all elements of that network are connected to other elements through the single device. In the old days, the device used to be hub. Now it's a switch. Of course, the problem with this configuration is that it's susceptible to failure of a central device, such as switch, but it's easy to identify, the failure and correct it. Then you have tree topology, similar to the star, but there is a hierarchy where you have like level 0 device or connector, then level 1. So there is some kind of hierarchy in how those devices are connected to each other. And then there is so-called mesh or mass, I guess, because mesh means that there is no particular topology. Devices are connected to other devices using some kind of random fashion. There's no particular mechanism or topology for connecting those devices. So a good way to describe this kind of mesh linkage is that devices are linked to other devices in multiple ways. Now, those networks, those topologies and networks based on those topologies, although they are messy and sometimes expensive to manage and configure, they are also very robust, because if there is a failure somewhere here, let's say in this point, then the message can travel to the same device. Let's say we're talking about those two devices and they're connected with this line, and let's say there's a damage in this line, so message can travel through other routes, and if there's damage here, it can find yet another way to travel to this device. So they're very robust devices, very robust topologies. Now, when it comes to network types, there are 6 general types of networks. You have the so-called computer telecommunications networks, you have local area networks or LANs, you have backbone networks, you have wide area networks or WANs, you have the internet, and also there's something called Internet 2 that is currently in development. So we'll talk about each of those types in a bit more detail. Now, the first type is the so-called computer telecommunication networks. This was the only type of network until 1980s or so. It was commonly used in mainframe architectures. Basically, this type of network means that the mainframe computer, this big powerful computer, is the network. There is a front-end processor that links all other devices from terminals and also peripheral devices into the mainframe. So basically, this mainframe is linking all those terminals and devices together into one single network. So the mainframe itself is the network. Another common type of, this one is not common anymore, but one common type of network is the so-called local area network or LAN. Standards for LANs, they were developed by the Institute for Electrical and Electronic Engineering, or IEEE. And IEEE 802 is a family of standards for LANs and metropolitan area networks, or MANs. There are 5 general types of LANs in common use today. 3 of them are wired, such as contention bus, token bus, and token ring. and 2 are wireless, such as Wi-Fi and WiMAX. And once again, there is a specific 802 IEEE standard governing each of those topologies, each of those types of networks. Now, the so-called contention bus network guided by standard 802.3 was developed by Xerox. It is usually called Ethernet after the original Xerox version of the standard. It's a half-duplex standard, and all devices must contend to use. And it uses the so-called CMA-CD protocol for collisions. It involves collision detection, but not avoidance. So if a signal collides, then devices can detect this collision, and then they can rebroadcast at random intervals to make sure that the message reaches the destination. Now, just one important element of this standard is that all devices must contend to use. In other words, the devices need to agree to communicate. That's different from some other standards, let's say internet, or I'm sorry, email standard, where you don't have to contend to receive an email. An email is being pushed onto you, and that's why you have something called spam, unwanted emails being sent to your computer. Now, some additional standards. You have token bus. A token is a special message that is passed among devices, and only the devices that have this token can transmit a message at a particular time. It's important for manufacturing automation protocol. It's important for making all those devices, from different manufacturers talk over one single network. And then you have token ring, like another variation of this idea of token. It's developed by IBM, and it has a combination of ring topology with the use of tokens. Used the same way as token bus. So those are like different variations of LANs. That are different variations of LAN standards. Then you have the so-called Wi-Fi LAN or wireless LAN. Wi-Fi stands for wireless fidelity. It's a very common wireless LAN type today, or standard today. It uses a shared Ethernet design. Means that Wi-Fi network is viewed as a complement or an extension of the wired LAN or wired Ethernet network. It uses a collision avoidance protocol. It's similar to collision detection protocol used by some of the LANs, but it has less collisions because it can actively avoid it. As you know, Wi-Fi is commonly used nowadays in offices to supplement wired Ethernet networks and support mobile devices or mobile workers in areas where adding hardware is problematic. Because by definition, wireless networks, they don't require wiring. You can send signal over air interface. So you can connect somebody outside of your business building. Many U.S. and international cities, they are offering Wi-Fi networks. Like for example, Wi-Fi networks are often offered in many international airports for free, so that passengers who are waiting for their planes, they can access internet. Then you have WiMAX. Now, WiMAX is similar to Wi-Fi. It's another microwave wireless transmission technology, but it operates over longer distances and the speed is typically higher. One critical element of WiMAX infrastructure are the so-called transmission towers. And those transmission towers, they can transfer wireless signal over several kilometers. So with WiMAX, the idea is that you can have those transmission towers covering large parts of a city, and you will need like a dozen of WiMAX towers to cover a town of a small size. It uses both licensed and non-licensed frequencies, and one of the common vendors in this area of WiMAX is Clearwire. Some implementation problems with wireless local area networks involving both Wi-Fi and WiMAX is that it's a very open network, and it's more difficult to secure than other types of networks. So basically, the transmission is over the air interface, and anybody who comes close enough within the area where the signal is broadcasted can, in theory, get on that network. Now, I told you earlier that a lot of cities nowadays, they have those initiatives to offer Wi-Fi for free. But there's always that problem with unauthorized access. Like a lot of organizations, like Starbucks or McDonald's, they would offer like free Wi-Fi for guests. But what's going to happen is that some people who are not legitimate guests, they would get access to this network, and they will keep using it, and they will overload it, with downloads and all those things. So Unauthorized wireless use is always a big problem for those kind of open Wi-Fi, public Wi-Fi networks. By unauthorized, we don't mean like some kind of security problem, just like some people will abuse, the fact that they can access this Wi-Fi network for free. And a lot of the times, I've noticed that a lot of good initiatives by the government, by these, local government, involving offering free Wi-Fi access in parks, airports, or some other public places, they don't survive long, because you always have those economic problems where the government decides to allocate a certain portion of budget to this particular initiative, and then they figure out that the usage of the Wi-Fi is quickly growing, and they cannot afford to maintain it anymore, so they introduce a fee, and that fee kills the entire initiative. So there are always like those business economic problems with those open Wi-Fi networks, public Wi-Fi networks usually. And that's why not all airports, what I've noticed, not all airports are offering free Wi-Fi. Then you have the so-called backbone networks. Now, backbone networks are basically ways to connect LANs together, and they're key to internet working, because basically internet, as we know it now, and we'll talk more about internet in a minute, the internet, the largest network that we have right now, is basically a network of networks. So you need to figure out how to connect those networks together. So in order for you to connect those networks together, you will use some kind of backbone network to link your network to some other set of networks. Typical backbone hardware devices include hubs. Now, hubs are not in use anymore because they don't have a very efficient or robust transmission algorithm. Because hubs transmit message from one device to all devices, and this is not very efficient. Then you have wireless access points. Those are central devices that connect wireless LANs to other networks. Then you have bridges that connect two LAN segments, and they only forward messages that are intended to another segment. For example, one message from one segment is being sent to another segment, another LAN, so that message is relayed. But messages within one segment, within one LAN, that are intended for recipients within the same LAN are not relayed to the second LAN that the bridge connects. Then you have switches, a multi-point bridge connecting two or more LAN segments together. Then you have a router that can connect two or more LANs and only forward messages to go to other LANs. So routers are very common when it comes to implementing the internet infrastructure. Then you have the so-called wide area networks, or WANs. They're similar to LANs but cover greater distances. They are the so-called long-haul networks. Now, there are three general ways to implement a WAN. There are switch circuits, dedicated lines, and packet switch. So I'll talk about each of those types of WANs, or wide area networks, in a second. Now, switch circuit means like this. This is like one way to implement a WAN. You have a single physical path that is temporarily created between two nodes for their exclusive communication. So, for example, when your computer wants to talk to another computer, let's say within the same corporate network but in a different city, then there's a temporary path created between those two nodes. The most common way of implementing this kind of WAN in a switched format is to use ordinary telephone network, to lease the service from some kind of phone carrier. Now, the advantage is that it's easy to set up because the telephone network is already there, it's already established. But the disadvantage is that you have low speed and high error rates because you're using those switch lines that are kind of configured ad hoc for you to transmit data. You never know which kind of line you're using, and sometimes you're sharing those lines. And there are two different pricing schemes available for this service. Typically, you have direct distance dialing, pay for usage, and then you have wide area telephone services. You have some kind of fixed rate per month. So here it's related to your actual usage of the network. Now, dedicated lines, another way to implement WAN, basically means you have your own line connecting two offices dispersed over a large geographical area. Those are like permanent channels, permanent wires allocated exclusively to your own corporate need. Now, the advantage is that they're high capacity, they have low error rates, but the disadvantage is that they're quite expensive. There are two different types of dedicated circuits. First of all, you have leased lines, that are kind of more or less physical. You have cables, microwave, or fiber connections, and then you have satellite circuits, and they are popular among organizations that have global locations. And then you have the so-called SONET technology. Those are fiber optics lines that are leased using a certain protocol so that several transmissions can be done, or several organizations can share the same kind of fiber optic cable at the same time. So circuits can be of different types. There can be they can be wireless, they can be fiber optics, they can be wired from regular cables and so forth. And here you have this is what I was talking about. You have basically billions bits or gigabits per second being transmitted through some of those fiber optics cables over large geographical distances. And then there's a packet switch way of implementing WANs. It's not really related to connection type. It's more related to the transmission protocol. So basically, what happens is that you have multiple connections over the same physical circuit. So it's not really about physical way of connecting it. It's more about transmitting. Packet switching is about transmitting signal over physical circuits. So basically, you have multiple connections among multiple devices on a network, and when messages are transmitted from one device to another, they're broken into packets or small chunks. And then businesses used pads, packet assembly, disassembly devices to connect their network to a common carrier network. So basically, you have a common network, connecting all those devices together, and then one network wants to send something to another network, so that message is broken into packets, and then those packets, they travel different routes, and eventually basically the message is disassembled into packets, and then those packets travel different routes. Eventually they're assembled at the source. Now the advantages is that it's efficient use of network, because those packets, they're small chunks, they can be sent through different routes depending on how busy a particular route is, and typically they have a large throughput overall. You can think of packets as like a freeway, right? Now, one way to send goods between, let's say, two cities is to build a dedicated rail line, and the advantage of the dedicated rail line is that you can transmit at once a large train full of goods. But the disadvantage is that it cannot be used by several trains at the same time, because one rail is just for a single train to pass. But packet switching is instead of using rail lines, you're using freeways, right? So freeways, they're shared by a lot of cars, and those cars, they're traveling different routes. If one freeway is overloaded, then let's say we're talking about a big city. If one freeway is overloaded, then cars will be directed to take another alternative route. So this is a very efficient use of the existing infrastructure. But the problem is that sometimes the speed, although the overall efficiency is good, the efficiency for individual messages, individual transmissions may not be very high, because some packets may be lost, some packets may be delayed. They may arrive in different orders, so disassembling and repeating those packets may require some time. So sometimes packet switching is a very efficient way to handle telecommunications, but it's not a very fast and reliable way to handle transmission. And then you have the internet, the most important type of network in use nowadays. It's a network of networks, and they use TCP/IP protocol for sending messages. It's like an enormous WAN, a wide area network. In 2010, there were 733 million hosts or devices connecting to the internet. I'm pretty sure that number is way over 1 billion. If you were following the news, you probably heard about that important milestone for Facebook, where they said that in one particular day they had more than 1 billion users accessing Facebook, in one single day. So that means probably that the number of devices out there is much greater than 1 billion. It began with the ARPANET project, the so-called Advanced Research Project Agency Network that was initiated by the U.S. Department of Defense. From what I remember, it was like a dual purpose project. On the one hand, they were saying that this internet project was about helping scientists from across the country to communicate, or even across the globe to communicate with each other using a reliable network. It was also, I think, positioned as a communication infrastructure that can withstand a nuclear strike, because internet uses the so-called mesh topology. Remember, we discussed it a few minutes ago. Now, the good thing about this mesh topology is that if one line is broken, let's say due to a nuclear strike, then you can still send messages using different alternative routes. So basically, each of these were, each of those kind of projects going two different ways. One for the Department of Defense, and then for the National Science Foundation. They were very large-scale packet switching networks. Eventually, they were kind of merged into one single network that is now called the Internet. Now, you know that a lot of interesting applications are built on the top of the Internet. We have, email. We have Usenet groups. We have listservs. You have file transfer protocol. The most influential one is probably World Wide Web, or the web, for hypertext transmission. Search engines, they're also, implemented over the internet, blogs, wikis, and, social networking. Now, social networking nowadays is probably the most profound application, the most important application built on the top of the internet. On the one hand, you have a lot of studies that basically say that social networks, they're dangerous. Some studies say that, at the minimum, social networks such as Facebook and Twitter, they waste people time. At the maximum, they develop certain psychological problems. First of all, narcissism. A lot of people, they start, after noticing that their friends are bragging about their new purchases and trips, in Facebook, they start thinking that this is what life is all about. It's about, buying something or achieving something, and then posting about this to Facebook to collect likes. So that creates like an, I guess, harmful mode of living for a lot of people. There are also some arguments that social networks are changing the way we think. They're changing our brain wiring. They're saying, there's a great article by somebody named Nicholas Carr published in The Atlantic, and the title of the article was quite provocative. The title was, "Is Google Making Us Stupid?" So what Nicholas Carr is saying in this article, he's saying that because of the social media nowadays, people have problems concentrating for more than a few minutes sometimes, or even a few seconds. So basically, now we're used to constantly receiving those small chunks of information in Twitter-like format, and because of that, a lot of people have problems concentrating on a book. For example, reading a chapter from a book becomes impossible for a lot of people because social media has changed the way our brain works, the way our brain receives information, because social media demand that the brain sends and receives all these small chunks, like small tweets, small Facebook messages, and that makes us incapable of processing larger chunks of information. But nevertheless, this is where this is where everyone is at nowadays on social media. So a lot of the times, people are saying, well, even if you don't like social media, you have to be there because that's where everybody's at, especially the new generation. I've noticed, like in my work, if you want to send, if you want to make sure that students receive your message, then email doesn't work. I mean, it looks like a lot of students, they're just ignoring their, whatever comes to their official university mailbox. And I've seen a lot of situations where like an important message is transmitted through email several times, and then 80% of students, they don't know about that message. So they're saying if you want to reach students nowadays, don't go to email, go to social networks. That's where everybody's hanging out and receiving messages. So like it or not, social media is here, and it's you who has to adapt to it, and not others. Then you have something called Internet 2. Internet 2 is basically a non-profit consortium made up of over 200 universities and some industry and government agencies, some companies and government agencies. The idea behind Internet 2 is to develop and deploy advanced network applications and technologies for research and commercial purposes. So basically, what they're saying that Internet infrastructure that we have nowadays is not good enough. It's slow, it's outdated, so there's a need to create a new set of standards and a new infrastructure for the so-called Internet 2 that would be a much faster, more reliable, and probably more accessible across the globe. So that's the goal of this Internet 2 project. I'm not sure how far they advanced this idea so far. So there have been a lot of talks about Internet 2 maybe 5 or 10 years ago, but I'm not sure whether this organization is actually accomplishing its goals or not. Okay, friends, so this concludes part 3 of our video presentation on chapter 3. So thank you for listening.